Bismillahirrahmanirrahim. This video is about discrete time convolution sum, and in this primarily we'll be solving end chapter problem number 2.6. Okay, so let's see the problem. Question 2.6. Compute and plot convolution yn, which is equal to xn convolution hn, where xn is given by this value and hn is shown as un minus 1. So let's try to have a picture of the input. First of all, we'll only plot this part, and so if you put n is equal to 0, so that is we are here, then anything to the power 0 will be equal to 1, so this value will be 1. If we go towards the right hand side, that is now n is equal to 1 here, so if you put n is equal to 1, then it will be 1 over 3 power minus 1, which will actually, if you calculate, it will become 3. So at n is equal to 1, it will be 3. And if you move towards the left hand side, that is n equal minus 1. So minus 1 minus minus plus, so power 1. 1 over 3 power 1 will be 1 over 3. So this is the plot of the first part here, that is 1 over 3 power n. Now what will happen when we multiply this by u minus n minus 1? We'll see that. So let's just revise the concept of un. Un is a unit step function, and in discrete time, when we write un, that means we are starting from 0, and at every interval of 1 we have a value, and the total value is 1. But if we put a negative sign with this n, that is u minus n, that means we are flipping this toward the left hand side, flip. So it will now go from 0 to minus 1, minus 2, minus 3, the value remains same. What about shifting? When we add a shifting, that is un minus 1, then what will happen? And the easiest way to understand is that if we put n minus 1 equals 0, then we get n equals 1. That means the starting point is from 1, not from 0 as it was here. So it will start from 1 and move to the right hand side. Similarly, if we shift the u minus n by minus 1, same logic now, we'll equate it to 0. That means n is equal to minus 1. So that is the starting point. So from minus 1, it will start and go towards minus infinity instead of a 0. And now what will happen when we multiply this and this? So you can see that 1 is from minus 1, and before that the value is 0. That means it will multiply this with 1, but it will multiply this or this with 0. So these two terms will vanish. And so the final result will be something like this, that the signal is starting from minus 1, then minus 2, minus 3, and the value is gradually decreasing. So this is the complete term or complete plot of xn. Okay. And now we go to the actual solving, and I'll strongly recommend that if you have not seen my previous videos on this topic, then you must see those videos, because a couple of things I'm assuming here that you already have learned. Okay, so this was our xn, and this is hn. And we have learned from the formula that xn convolution hn can be written in this form: summation xk multiplied by hn minus k. Now how do we get these two terms? This can be easily found by replacing n by k. So from here if we replace n by k, we get xk. So let's see that. So we replaced by k, so it will now become xk. This power will now become minus k. U minus 1 n will become minus k. So this is the after changing the variable. What about hn? Now look here in the convolution sum, the n has been shifted by k. So whatever is the value of n here, that will shift by minus k. And so this was this value x, and this hn will be shifted by k. So it will now be n minus 1, which is n minus 1 and minus k. Okay, so now this is the shifted hn minus k, and this is xk. And this, after plugging in the values of xk and hnk, this is the yn values. Now, as we have learned in the previous video, the procedure that I follow is that after we have flipped this one to the other side, we move this whole thing to a point n, which is far away from n. So let's see in the next slide what will happen. Okay, so this is xn. We have moved hn minus k to far away to a point n, which is far away from 0. And then we gradually pull it towards right, and we see the overlap. Now because this is extended up to infinity and this is also extended up to infinity, so one of the limit point is infinities. And from infinity now you can see there is a complete overlap. We have to determine a point where this complete overlap ends. So let's see, we keep pulling, and when we come at this point where n minus 1 is equal to 1, this is the end point. After that, if you pull it further right, this one will go out. So now there will not be complete overlap. So this we call is the second limit. And this condition is happening when n minus 1 is less than equal to minus n. Minus 1. N minus 1 less than equal to minus 1. Okay, the limits. The limits of summation are from minus infinity we coming, and where we are stopping at n minus 1. So this is the limit. And so the yn formula we can now write. Yn is from minus infinity to this limit n minus 1. Value was 1 over 3k, which is this, multiplied by 1, which is this. So this is our final equation. We call it equation number 1 for the convolution when up to a point n minus 1. Now let's see what will happen if we move it further. Okay, so the moment we move it further, this thing goes out. This is up to infinity, so this is also up to infinity. So one of the limit is infinity, no doubt, but what will be the other limit now? Now you can see when we are moving, we don't know which point is coinciding with this. Is it n minus 2, n minus 3 or n minus 1? So we are not sure. That is why instead of taking n minus 1 or n minus 2 as limit, we'll take the limit from the upper diagram. We know for sure that for n minus 1 or n minus 1 greater than minus 1, the overlap will end. So this is our limit. This is the second limit. One was the minus infinity and the other is minus 1. This is the limit, and so we'll write that the summation limit is k is equal to minus infinity to k is equal to minus 1. And the condition now is, when is this happening? When we have moved n minus 1. If you look here, if we have moved n minus 1 beyond minus 1. So n minus 1 greater than minus 1, or from here we can also write that n is greater than 0. This is the condition. So utilizing this limit, let's write the formula now. So the limit minus infinity to minus 1, again 1 over 3 is the same value, 1 over 3 minus k, and here also we're still multiplying by this value 1. So this is our second equation, and now let's see them together. So for n minus 1 less than minus 1, or n less than equal to 0, this is our equation. And for n greater than 0, this is our equation. And just compare the two, the values are same, only the upper limit has changed. It's starting from minus infinity, minus infinity. This one is ending at minus 1, and this one is ending at n minus 1. Okay, now we need to simplify these two equations to find the final result. And that is the toughest part, so you have to be very patient. Okay, our aim is to achieve the infinite geometric series formula, this value, when the limit is from k0 to infinity and a r power k, then we get a divided by 1 minus r value. And the condition is that this value r, it has to be between minus 1 and plus 1, but it cannot be 0. Okay, now let's consider the first equation. This was the first equation that we got, and this is the infinite geometric series formula. We have to convert these equations to match this part. Now, what are the mismatches? Let's see. We have minus k here, we have a plus k here. The formulas or the limits are also different. So let's first tackle this one. And the technique that will follow is we replace minus k by a new variable m. And so this will become positive m, so it will match rk 1 over 3m. Okay. What will be the effect of this replacement? And the limits. So the limit is from k minus infinity. K is equal to minus infinity, putting minus sign on both sides, so it will be minus k is equal to positive infinity. And minus k is actually m, so the one of the limits become m is equal to infinity. And what about the other one? K is equal to n minus 1. Again putting minus on both sides, so minus k is minus n plus 1. Minus k is m, so m is n minus 1 plus 1 or 1 minus n. So now let's rewrite. So yn will be m 1 to n from 1 minus n, and the other limit is infinity 1 over 3m. So this part is now matching, but here still is a mismatch. The upper infinity also matches, but we need to have a 0 here to be perfect match. So how do you bring a 0? If you see, if we take these two terms on the left hand side, then it will be m minus 1 plus n is equal to 0. And if you put that term equal to another variable p, then we can achieve the desired results. Let's see. We want to match it with this. So just like I'm showing here, we have taken all these two to the left, so m minus 1 plus n, and this is equal to 0, and if you call this equal to p, therefore p is also 0. So we can write it, p is equal to 0, and what about the upper terms? When m is infinity, like it is in this case, then anything plus minus with that will also be infinity, therefore p will become infinity. Now what will happen to m here? This m from here we can write that m is p minus n plus 1. So this one has changed, but we can manage this. Let's see how to do that. If we break this, we can write it as 1 over 3p, and the second term is 1 over 3 minus n plus 1. Now minus n plus 1, or the second term, is not dependent on the summation because the summation is with respect to p. So this is constant, we take this out, and now what is left is this term, and this exactly matches the infinite series. Therefore for this we can write a value in this form. Let's do that. So the constant is out, and now 1 over 3, a is 1 in our case, there is no a, so we assume it to be 1. So 1 divided by 1 minus r is 1 over 3, and if we solve this from here, it will be 3 over 2. 3 minus n plus 1 can be written as 3 minus n into 3, and this is the multiplication term, and after solving, this 3 and this 3 gets cancelled. So, and this 2 will come at the bottom, and 3 raised to the power minus n we can take it to the numerator, so it will become 3 raised to the power n. So this is the final answer for equation number 1. And so we write that yn is 3 power n divided by 2 for n less than equal to 0, and this we call equation number 3. Now let's solve equation. Okay, now let's consider equation number 2. This is equation number 2 within this limit. And here also we compare with the infinite series equation. Similar differences, we have minus k here, we have plus k here. So we'll again replace this minus k with variable as we did in the previous slide. We replaced it by m. Here we can choose another variable just to distinguish. So let me select a variable q. So replacing minus k by q. So minus k we replace by q. And here if you put minus on both sides, so minus k will be positive infinity, and minus k is equal to q, so it will be q is equal to infinity. And for this, if we say that here k is equal to minus 1, that means again putting minus on both sides, so it will be minus k is equal to 1, and therefore q is equal to 1 is the other limit. So this is now perfect. We have achieved this portion, but we have not achieved the second part. We can invert this, we can write 1 here and infinity, but still there is a difference. We should have started from 0, but it is from 1. So there is a simple technique to solve this problem, and let's see here. We know that if we have a limit from q0 to infinity of any value, then this can be divided into two parts. We can take out the first part, that is we put the limit q here. So this is q is equal to 0 here, so we put the limit 0, and now what is left of this is from q1 to infinity. So, and now anything to the power 0 is 1, so we can write it as 1 plus this part, and now from here we'll just manipulate. So this can be written as q0 infinity, and we bring this towards left hand side, so it is minus 1. So this portion with a q1 can be replaced with q0 with a minus sign. Okay, so this is how we have manipulated, and now you can see this is directly matching with the infinite series. So now we'll plug in the values according to the formula. So 1 and that is a is 1 divided by 1 minus r, which is 1 over 3, and minus this 1. Solving, we get an answer of 1 over 2, and this is valid for all values greater than n greater than 0. So finally, this is our result. We have the output yn 3n divided by 2 for n less than equal to 0 according to equation number 3, and 1 over 2 for n greater than 0 according to equation number 4. And now we can very easily plot this. Just take couple of values for the upper one. If I take n is equal to minus 3, then minus 2, then minus 1 and 0, because it can only go up to 0, so we get these values. And similarly for this one, since it is going from greater than 0, so we'll take value of n is equal to 1, 2 and 3, and from here we get value of half in all the cases. This value we just put in here. So when n minus 3, then 3 raised to power minus 3 divided by 2 will get 154. 3 raised to the power minus 2 divided by 2, we get 1 over 18, like this. Okay, and now very easily we can plot this. You can see from n0, this point, it is half, and then it is gradually going down, and the other one is remaining constant half. So this is the final plot of yn. So I hope this gives you an understanding how you can solve this type of a problem if you follow these steps. Thank you.